Welcome back to week 5 of our course, Boltzmann Law, Physics to Computing. This is the 4th lecture for this week. In the last lecture, we talked about this Grover's search algorithm, which makes use of these quantum transformations to do the search. It gives you a very efficient search algorithm. In this lecture, we'll talk about another celebrated quantum algorithm, one that allows you to factorize large numbers efficiently. Now, the way this works is, supposing I want to factorize a number f, then the first step is to find the period r of the function a to the power x mod f, where a is a number you can choose arbitrarily, any number you want, and what you want to find is the period of this function. So let's look at an example, and that would make it clearer. So, because the difficult part when f is a big number is to find the period of this function, and that's what the actual algorithm does, is it uses quantum circuits to find the period. But if you have the period, then how would you use it to get the factors? Let me first describe that. So supposing I'm trying to factorize 15 and I choose a equal to 11. So now when we write down this function, so this axis is x. So when you put 11 mod 15, that's 11 to the power 1 mod 15, you get 11, that's this. Then you go 11 squared mod 15, that's 121 mod 15, that's 1. So you're down here. And then you go to 11 again, and 1, 11, 1. And so it's a periodic function, and the period is 2. So every 2 times it repeats. Now, as I said, a is not unique. You can choose a any way you want. So if you chose a equals 7, then you'd get a different period. So 7 to the power 1 mod 15, that's 7, that's this one. And 7 squared is 49, mod 15, that's 3, that's this one, and so on. And you can see that it will repeat after a period of 4. Now, once you have found the period, and that's what the Shor's algorithm will let you do for large numbers easily. Once you have that, then how do you find the factors? Well, the rule is you find the greatest common divisor of these two quantities, the number you have and this a to the power r over 2 minus 1 and a to the power r over 2 plus 1. So for example, in this case, a is 11, r is 2, so r over 2 is 1. So we have 11 to the power 1 minus 1, which is 10. And the greatest common divisor of 10 and 15 is 5. Similarly, 11 to the power 1 plus 1, that's 12. And the greatest common divisor of 12 and 15, that's 3. So the factors are like 5 and 3, which is of course the correct answer for 15. 7 also would get you the same answer, but in a different way. Here r over 2 is 2, so 1 is 7 squared minus 1, 15. 7 squared minus 1, that's like 48 and 15, and again the common divisor is 3. Or 7 squared plus 1, that's like 50, and 50 and 15, the common divisor is 5. So again you get the correct factors. So that's how the overall thing works. Now the point is to find this period. Okay. So the way this would work with the quantum circuit is, you have a main register where you have a certain number of bits, and I've chosen 4 in this case. Actually you'd need more to do the 15, but just to keep it kind of not too messy. As you can see, it's already with 4, I've got 16 components, so it is kind of hard to see the thing clearly, right? So I just kept 4, and then you have an auxiliary register which also has 4, let's say. So you start off with both in the 0 state, which means that the top item, the first item, has an amplitude of 1, rest are all zeros. And there's 16 of them, just so you can easily recognize which component we are talking about. I've put a red marker after every 4 of them. So the 4th one is red, 8th one is red, and the 12th one is red, and the 16th one is red, right? So, and we will think of it as 0, 1, 2, 3, up to 15. Okay. The first step is do the Hadamard transformation, and that we have discussed it often enough that you know immediately what to expect. You just have 1 spread everywhere, and there's the 1 over square root of 2 to the power 4 in front. Okay, so we have this, and then of course there's the auxiliary register which is still in the 0 state. So the overall state of all 8 would be like these 16 chronicled with these 16. So if I had to write a complete wave function, it would have 256 components. But it's more convenient to write it in 2 parts, like the 16 here and 16 here. And if I had to write the full wave function, I'd take the Kronecker product of the 2. Okay. Now, these 16 then, let us divide it up into 2 parts. So, in the first part, we keep the alternate ones, like a 0, and then the 2, and then the 4, and then the 6, 8, etc. And for the other component, we keep the other ones, 1, 3, etc. So we are kind of separating it out. Now, why are we doing this? Well, that we'll see in a minute, how that helps. Okay. Now, the point is that when you separate it out, then these 2 sections have a different corresponding thing in the auxiliary register. Why is that? Well, because you see, what we are going to do is apply a gate, something that performs a transformation, so that if you have x here, it puts f of x into the auxiliary bit. And remember, for our example, f of x is either 1 or 11, and it is 1 for one set and 11 for the other set, right? So that's why we separated it out, because what this gate does is it takes this one and it corresponding to all of these components, the auxiliary is 1. Whereas for all these other components, this one is 11, and that's why it has a 1 at the 12th position. Remember, this starts from 0, so 0, 1, 2, 3, 11 is at the 12th position. So overall then, after applying this gate, what happens is half the items get involved, are chronicled with 1, and the other half are chronicled with 11, right? And of course, this is because the period was 2. If the period had been 4, then I'd have 4 terms to write. In fact, I kind of chose this one so that I can conveniently write it out cleanly. So I have these 2 parts to it. And so the overall wave function then is this Kronecker product with this plus this Kronecker product with that. Okay. Next, what you apply is what's called the quantum Fourier transform. And what the quantum Fourier transform does is it takes something like this and produces a set of coefficients which are the Fourier transform of the original coefficients. So here, because this is a periodic function, when you take the Fourier components, you get peaks. So, and there will be 2 peaks because the period is 2. If the period was 4, you'd have got 4 peaks here, and so on. And the interesting thing is you get essentially the same structure for both of them, for both this and this, because these are essentially the same function but shifted over a little bit. Here the plus 1 is on 0, 2, 4, 6. Here it is on 1, 3, 5, etc. So it's just shifted. And what is well known in the context of Fourier transforms is that what a shift does is it doesn't change the components. What it does is changes the phase of the components. So you get some complex number here, and that complex phase is different for the two, but they both kind of basically have two peaks. So after doing the quantum Fourier transform, then what you have is that the main register has got two peaks, and one of them is Kronecker product with 1 and the other has a Kronecker product with 11. So those are the two components. And now if you come in and measure the main register, you'll see two peaks. And when you see two peaks, you conclude that, hey, R is equal to 2. And remember, that was the original purpose, to find the period R so that you can then go ahead and find the factors. And this is where you see if you had 4 of them, what would have happened is there would be 4 terms here, but then when you Fourier transform it, you'll get 4 peaks, and that's what would appear here. And with large numbers, of course, there will be many more peaks. There will be long periods, and that's when you really need these special algorithms to find it, right? And that is when finding it directly would have been more difficult if you had huge numbers. But ideally, this quantum circuit will find the peaks for you. It will give you these specific peaks, and then when you measure it from those peaks, you can then deduce the period. Now, what does this quantum Fourier transform look like? Well, the basic transformation would look something like this. This is basically the Fourier transform. The idea is you take the different components, and when you calculate the output, the first column is all ones, next one goes 1, p, p square, etc. The next one goes 1, p square, p4, etc., where p is this phase factor. And this is exactly the definition of Fourier transforms. In fact, it would be like a digital Fourier transform, discrete, when you have discrete samples. So you're transforming the coefficients of all these different states, right? And that's what this QFT does. So, and you can check how this works. Supposing you have this QFT, in this transformation U, you multiply it by something that has alternating plus ones. You can check that if you do this, you'll get zeros everywhere except for these two positions. Okay? Otherwise, because when you do this, what do you get? Well, for the first item, you get all plus ones. So it means you are adding these all up. So you get a big thing. Next time, you are multiplying it with a certain phase factor. This is a phase of 2 pi over n. And there's another, and so you get 1 plus p square plus p fourth, etc. And since each one has a phase, when you add it up, actually you end up getting a 0, etc. So you can check this out. You'll get zeros, but then again you'll get a peak after a while. And that's how the Fourier transform would work. And if you were to put, instead of ones in the position shown, if I had moved it over by 1, you'd have got the same structure but with a different phase. Okay? So that's how the QFT works. So overall the picture is something like this. You start with the 0 state for both registers, apply the Hadamard, so turn the main register into this complete superposition. Then you do this transformation, which anytime there's an x here, it associates it with a f of x here. And then you do the Fourier transform, so the x becomes a k, which is associated with the f of x. And this is where, when you look at the peaks of k, it tells you the period. Right? So that's the overall structure of this thing. And again, if this was a course on quantum computing, then the next point we would be discussing is how do we implement these gates with how do you implement these transformations using of the order of n gates? Because again, if you need 2 to the power n gates, then it's not very useful. But people have worked out concise ways of the order of n gates, how you can do this QFT transformation and how you can implement this other transformation that I talked about, which takes a x and associates an f of x with the auxiliary register. So these are things we won't be going into, because my main point was to show that how these quantum algorithms make use of interference, make use of complex numbers to get peaks in the result, peaks that give you the correct solution. And that is very different from what you can do with classical circuits. So in summary then, again, we have gone through these, we started with the Hadamard gate in 5.2 in the second lecture, and then we talked about 2 of these celebrated quantum algorithms, not in great depth, but the main idea was to illustrate how it uses these transformations with complex numbers actually to get peaks that help you do something useful. And in the last lecture then, we'll finish up by pointing out how this use of complex numbers is really what differentiates quantum algorithms from the classical ones, and why that makes it particularly useful, why that provides really the motivation for developing quantum computers. So see you at the last lecture for this week and for the course.